Welcome back to Gabversity, where facts don't care about your feelings. So, what are we going to do today? Well, we have a little wave function to solve. And based upon yesterday, if you guys remember the free particle, there was a way to describe that wave. And the way to describe it was in terms of the integral of all the possible wave fingerprints, which is k, the number k, right? So how do we do that? Well, I'm going to show you. There's going to be a few things involved. There's going to be integration via double substitution. And double substitution just means that we're going to change the language of mathematics along the process. Because sometimes it's easier to solve a problem in another language than within one language, if that makes any sense. And we're going to complete the square. Completing the square that's from high school. If anyone knows, a plus b all squared equals a squared plus 2ab plus b squared. All right, and we're going to put it into that form. So it's, to give you a rough example, it's sort of like if you look at the Islamic calendar and the Western calendar, and they run at different rates, right? But you can convert from one to the other if you want to solve a few problems. So if you want to know how long before the next Ramadan, for example, you could convert it into the Islamic calendar, then check, and then convert back, right? That's just an example, and that's what we're doing today in the mathematics. So let's begin. Here is the problem. Right? The problem is, right, that we have a wave function, and it looks like this. You ready? This is x0, and if you guys remember from last ones, that's a snapshot at the time equals 0, equals a e to the minus ax squared. Hey, Scott's here, Captain's here, everyone's here. All right, so that's what we have. Now this is quite interesting, because if you guys remember, right, how do you solve this problem? This is a free particle, right? If you remember from yesterday, we said free particle. All right. Now, what is the point of a free particle? Well, we said yesterday the free particle, let it go and it just turns into this infinite wave. So how do we find it? Well, what we have to do is we have to put it in terms of this. I'm going to show you, right? We're going to put it in terms of, right, it has to go in terms of this, right? Which is xt, right? That means this is the wave. This is a two-dimensional wave. That's only one dimension, because that's just the wave in one dimension, and we snapshotted it at time equals 0. Now this is for all time, for the past, present, and future, right? And we worked out that it should be, from memory, 1 over square root of 2 pi. Hold on, let me check if I'm right. Yep. And then the integral from minus infinity to infinity of all possible wave fingerprints, right? So that's 5k. Site, you can call it, 5k. And then by the time component, which is the other dimension, which is e to the power of I, k, x, and k, x is the distance, k is the fingerprint, right? Minus omega t dx, dk, sorry. Let me just, hey, paint something's here. Let me make sure I've got that right. I have that right. And this here, if you remember, is the spin, right? The angular, sort of like an angular velocity type of thing, right? So where, I'm just going to put semicolon, where omega, which looks like a W, hello, equals h bar, which is the pixel size of the universe, k squared, which is the wave fingerprint, over 2 times the mass. Let me make sure I'm right. Yes, I am correct. Excellent. All right, so this is the equation that we want to get to, right? So we want to go from here and reconstruct the wave for all time, right, into this form. So if you remember, right, I completely forgot what I was going to say next, but anyway, that's what we're going to do. If I remember, we'll come back to it. All right, so let me jump in. Now we want to find the equation, right? It's called a function, right? A function, it's like an equation in a way, and it tells you where all the fingerprints of all of those infinite mini waves are. We spoke about this yesterday, right? Or it might have been today for you guys. Okay, so where is that? I will show you. It works out to be right here. Ah, there it is. Okay. So it works out to be this thing here, this phi of k, right? That here are all the possible fingerprints, right? So what we're going to do is we're going to say phi of k, right, equals, right? And if I can remember, it is 1 over 2 pi, square root of 2 pi, integral minus infinity to infinity, right, of, I'm pretty sure it's the wave function, wherever it is. Where did I put it? I don't know where I put it. E to the minus ax squared. Yeah, it's the wave function, which is this, right, at x0. Okay, so that's the stationary wave. We took a snapshot of the wave in 1 dimension, right? We haven't done 3 dimensions yet. And in the future, in a few weeks, when we do 3 dimensions, that's going to be a 4-dimensional wave, which is going to be pretty cool. All right, so this is the original wave, right, of the free particle when we let it go. Remember, we let it go. Right at that instant, there was a wave. We put that wave in here because to get this, right, multiplied by, if I remember, do I remember? E to the minus ikx. Okay, so e to the minus ikx, and it should be dx. All right, so now we have an integral. Now that's I is that multi-dimensional or 2-dimensional number. K is the fingerprint and x is the distance, okay, or the location of the particle. Okay, so this is now the equation to get this. Okay, so far we're building up this equation, and the reason we're building up this equation is because we want this, and then we're going to put that and that to get the full equation. All right, so far, just confirming, so far we have the wave at time t0, at the instant we let the particle go and it just disappeared into a wave. We have that, right? Then what we need is to build the wave for all time. We need the function that tells us all the possible values of k, which is the fingerprint, right? Now, so that's the next step. We want the fingerprint function, if you want to call it that. It's called phi of k, which is fingerprint function. Now, how do we get the fingerprint function? Well, we put in the original wave, that one, and we integrate it, right? And multiply by e to the minus ikx. So that's just mathematics, okay? And we've just written that down. Okay, so now we're going to do the maths. And now we're going to run into some problems. And this is where we're going to do mathematics to solve the integration. And it's called integration by double substitution and by completing the square. We're going to use all 3 of those things together. McDoodah. Right? And as I said before, double substitution, it's like switching from, for example, the Western calendar to the Islamic calendar and then to the Chinese calendar. You solve the problem in the Chinese calendar, you bring it back to the Islamic calendar, solve the problem there, the next part of the problem, and then bring it back into the Western calendar. There's your full solution. Right? And it's sometimes it's easier. It's like, for example, let's say that your first language is, Greek. So it's easier to translate the problem from English into Greek, solve the problem, and then put it back into English. That's what we're doing, because mathematics has many sub-languages, right? And you'll see now. Okay, so this here, right? This here is that, okay? So that equals, right, 1 over 2 pi, root 2 pi. Stop, you make it seem too easy making people's heads. It's not that hard. Now I'm actually doing the language. If you know the language, I mean, it's basically what I was saying. It's not that difficult. Anyone could do it, honestly. I've tutored people, who'd had no idea of maths, and then after a couple of years, they're like smashing it. So minus infinity to infinity, all right? This, right, which is that. So a e to the minus ax squared e to the minus ikx dx. All right, so all we did was sub that into that. Now, this is where you're not gonna, if you haven't done maths, you're not gonna follow this word for word, because it's like if you haven't learned Greek and I start speaking Greek, it's like, what is he talking about, right? So, but that's okay. But if you've done calculus and you've done integrals and you've done some high school maths, then this will make sense. But if it doesn't, it's okay. You can follow on, and then at the end you'll see the final answer, and I'll show you how we got there, right? Okay, so that, right, equals this. Now we're just doing some mathematics. We're just rearranging stuff, right? Okay. Then we're going to take the a outside because a is just a constant. Okay. If you know integral calculus, you'll know what I mean. A is just a constant, take it outside. And then this thing we can combine into this. E to the minus ax squared plus plus ikx, yes, that's right, dx. All right, so all I've done is I've simplified that into this. Okay, so now we have a problem. How the hell do we integrate this thing? Because that looks way too difficult, right? Well, easy. What we do is we simplify it. Now, how do we do that? Well, I'll show you. This is now called integration. This is now called integration by substitution, right? So as I said, you know, we have something in English which is like a really long sentence. We move it into Greek, which might only be one word, and that's what we're doing now, right? So we let where are we? Y. Where am I here? See where I made my notes before. Okay, we let y by definition, so y equals, and there's 3 because we're making it equal this, we're forcing it, right? We let y equal root a, okay, outside of x plus b over 2a. Now, why do I do that? Okay, so this is now part 2. Okay, now let's forget what we were just doing at the moment. This part, the first part's done. Okay. So now what we're going to do, we've gone up to here, right? We're going to convert this into language of y. So at the moment, right, the language is in x, right? So for example, let's say we're working on measuring a shelf. Let's say we want to measure a shelf, and let's say McDuda's like, I don't know, McDuda's a tall bastard, isn't he? He's like 6'5" or something. Oh, great, another truck. Why are trucks coming to this? What is going on in this little no-through road that has all these trucks coming in? Amazing. Anyway. All right, so let's say McDuda's 6'5", right? So if I want to measure a shelf that's 6 foot, right, and I only have McDuda to use as a measurement, right, it's going to get confusing because I'm going to have to say, well, the measurement of the shelf is McDuda divided by 6'5" and then times by 6. It's difficult. So what I do, if I have a shelf that's 6 foot tall, what I do is I get someone who's 6 foot. So maybe I get paint something. I'm just guessing your heights, right? So let's say paint something is 6 foot tall. I'll say, okay, I'll use paint something to measure the shelves. And then once I get the measurement of the shelf, the final measurement of all the shelves I can put back into McDuda form, right? That's all I'm doing. What a waste. What is it? He drives up the street and back to clean it. What is he cleaning? The government, mate. All right. So what I'm going to do is I'm going to switch it from terms of x into terms of y. That's it, right? So those who know mathematics understand what I'm saying. Okay, we're going to let y equal this. Why is that important? Why? Why is that important? Because this implies that y squared equals, okay, it equals ax squared plus, what have I done here? I think I've done something. What have I done wrong? Think, Abby, think. Plus, I think I've made a mistake somewhere. Let me check my other notes. Oh no. No, I think I've done that right. So ax squared plus, and then that becomes b over root a plus, no, b over root ax. What have I done wrong? Freaking hell. Plus, and then that's, I think I've done something wrong. Damn it. Let me go slowly. So therefore, y equals root ax plus, lol, don't give up. Nah, I never do, never have. Root, so b over 2 root a. That's it. Okay. I think that's correct. Okay. So therefore, y squared equals ax squared plus, what have I done? No, I've made another mistake, have I? Oh, no, I haven't. No, that's correct. Excellent. Plus 2 by that cancels out. That becomes bx. Excellent. Plus, and then this squared, which is b squared over 4a. Excellent. All right, now why have I done this? I've made that y squared, and that's because, so therefore, ax squared plus bx equals y squared minus b squared over 4a. Now that is quite interesting. Why is that interesting? Well, because look at this. Ax squared plus bx happens to be right there ax squared plus ikx, and you can just make ik equal to b. Right? So that's going to be our second substitution, right? And we can put that into here, and once we put that into here, then it becomes very easy to solve the problem, which is quite interesting. So now, right, what we're going to do is we're going to say, now we come back to this original equation, right? So that means, right, that implies that the original equation, 1 over 2 pi all square rooted, oh yeah, square rooted, right, that a outside the integral minus infinity to infinity of e to the minus ax squared plus ikx dx, okay, we can now solve this equation. All right, because we know that that equals y squared minus b squared over 4a. So we just translated the language, right? Equals 1 over 2 pi, okay, 1 over 2 pi, sorry, there we go, a integral from minus infinity to infinity, right, of e to the minus y squared minus b squared over 4a dx. But now we have another problem. The problem is that we are now integrating with respect to y, but it says with respect to x. So how do we fix this? Well, what we've got to do is we've got to find dx, so which is the derivative of x. And if you guys remember from before, the derivative is like saying if you have someone's position, you can find out their speed. The speed is the derivative, right? That's the analogy, right? So we know the speed of x, but we want the speed of y, right? Hey, God is dead, man. Some gangster invites. Hey, hey, hey. How do we get the speed of y, right? We want to convert the speed of x into the speed of y. Okay, so, you know, for example, as I said, if you look at the Western calendar, we travel at 365 days per year, whereas the Islamic calendar travels at around 360 days per year, right? So they are traveling at different speeds. So we have to find what's one speed with respect to the other. So maybe the Western color is like 1.1 or 1.2 times the other one. So we're just switching from one language to the other, so we have to know the speed. All right, so let's do it. We know, right, since, right, y equals, by definition, root a by x plus b over over 2a, right? This implies that dy, right? dy, so the speed of y, is going to equal, right? And this is just basic derivatives now. Derivative of this would just be root a, and derivative of that is 0, right? So it equals that dx. In other words, the speed of y, right, relative to the speed of x is root a by root x, root a by dx, sorry. So, you know, maybe McDuda's driving his truck at like 60 miles an hour, and I'm driving my car at 70 miles an hour. So my speed relative to McDuda's speed is like, I don't know, 7/6, right? So 7/6 times McDuda's speed. That's all we're doing, right? So now we just do a bit of algebra, and then we say, so therefore dx equals 1 over root a dy. All right? Now that's awesome, because now, see dx up here? Now we can just swap in that and put it up there. All right? So this implies that 1 over 2 pi all square rooted integral minus infinity to infinity. I think my pen is finally dying. My favorite pen is dying. No. All right. E to the minus y squared minus b squared over 4a dx actually equals, it actually equals 1 over 2 pi all square rooted minus infinity to infinity integral of e, so this is all the same, minus y squared minus b squared over 4a dy over root a, right? So now we've switched it into dy over root a, which is the same, if you remember here, dy over root a is the same as dx. So we've now switched it, right? And this is awesome, because this integral is exactly this integral, but we've converted the language. Supernova, long time. We've converted the language from with respect to x, so McDuda's speed, into paint something speed, right? So she's moving at root a, so the speed of McDuda divided by root a, isn't it? Root a, sorry. This is paint something speed. She's moving at root a multiplied by dx. Hey, welcome back. All right, so now we have this equation, which is way easier to solve than this equation. And that's because for those who've done calculus, this equation here, you have an error function and you have another value of x, and they're multiplied together. All right, they're two separate wave functions multiplied together. Here, we've only got one wave function with respect to y. All right? So it's way easier. So for example, to give you an example, maybe McDuda, he's driving his truck and he's got like 2 carriages on the back, right? So it's hard to calculate, you know, if he turns left, where's that? But if we go to paint something, maybe she's just driving a bus. So it's easy to calculate because it's just one fixed unit. So we find out her movements, and then because her and McDuda are going together, we can convert it at the end and figure out where McDuda must have gone. So we're just changing the language, that's it. All right. All right, so the integral of this, right, we just use this one becomes, I'm going to simplify it again, make it even easier, right? This, right, equals, yeah, exactly, Miss Supernova knows her stuff. This equals 1 over 2 pi, okay, integral of minus infinity to infinity of e to the minus y squared multiplied by e to the b squared over 4a over root a dy. Now what have I done here? All I've done is I've converted this to this, because there's a minus sign. That's e to the minus y squared, which is here, and that minus and minus makes a plus, so that becomes e to the power of b squared over 4a. And if you know your index laws from high school, then that times that, there it is, right? So it's that function by this function, right? But here's something now that's, hey, Shubi, long time. Now here's something that's even more interesting. So what we've done is we've made it now one function by another function. But here's something, you have 11 quite focused students, listen, Professor Gab. So, y, the second function doesn't have a y in it, right? So if it doesn't have a y, then it's not a function, it's just a number. It's just some random number, which is awesome. Because as we know, right, we don't have to worry about integrating that. It's just a constant. It's just some random number. So, you know, it's like saying, for example, 1 plus 2 plus 3 divided by 6 plus 7 over 3, you know, multiplied by, you know, all of that is just some number. It equals a number. It doesn't change, right? The speed is, there's no speed. It's just standing still, right? Okay. So now we can make this equal C, right? So we can take this and we can just call it C bar, right? Just some other number. And why is that important? Because that makes this whole equation really easy, right? I think I've missed an A somewhere. I have missed an A. There should be an A there in the equation. Sorry, I forgot the A. So I can get it into exactly Roger Mo Appy. Exactly dead on, my friend. So that can now, that's now times C, and you can put the C out here. So that becomes 1 over 2 pi, right? Square root multiplied by A multiplied by C bar. Okay. Integral of minus infinity to infinity of e to the minus y squared dy. Look at that. Look how much simpler that is now, because that's outside of the integration. So that's just some constant. All we have to do now is integrate this. How easy is that? Right? So that is really important. This is important. So look what we did, right? We went all the way from here, this whole freaking crazy thing, right? We put that into this. You do math for fun. I do math for fun. Yes, but I'm doing research into quantum mechanics, so I've just got to brush up on my quantum mechanics for next year. Looking at getting a scholarship from the uni to do some research in quantum field theory, which would be pretty cool. And must be a genius or something. Well, if you go to YouTube Gabsmacked, you will see my second live speech on autism and my book, which is called Tragedy of the Retarded Genius. So interesting. Okay, so a very observant guy. And hey, Lupus Comicus, hello. All right, what is the point of all that? Well, the point is that we've now solved this damn equation, which is about frickin' time. So here's something I prepared earlier. Right. That's what we got to. Gonna follow even though I understand nothing. The sun looks refreshing. It is beautiful. Let me show it to you. Oh, whoops, that's my face. Sorry. There you go. And you can see that we're in winter because the sun is angled towards the north. It's angled too far north for us. Whereas in the summer, that sun, instead of being over there, it'll come almost overhead. Yeah, it'll be crazy. Our summers are so bad. In fact, southern hemisphere summers are hotter than northern hemisphere summers. And because of our strong Arctic current, it doesn't get cold because the water is cycling to the point, a lot of neutrons there. Yeah, in the sun. That's true. There's a lot of neutrons in the sun. This is true, my friend. All right, so let's get back to this. So we were able to then, let me get this into focus. Nah, don't be sorry, my dear. It's always a pleasure. I get distracted very easily. This is why I got kicked out of school so many times. All right, so we got that. So now we know the integral of this, and that's an easy integral because all we have to do is go to our integral table. And I've proven this one before in another lecture. I think it's called the error function. If you look at my error function lecture. Oh, by the way, there's a new website thanks to the Dome Father, and it's called Gabflix for your daily Gabfix, and all our channels are there. And it's bit.ly/Gabortisavant, GABAUTISAVANT, Gabortisavant. And you go in and you've got all these YouTube channels, like you can see all the, you can smell good math. You must have some skills, my friend. So you can go there and you can see all the replays, and you can get the mugs and the pens and whatever else. I don't know, he does it all. I don't really know exactly how it works yet, but it's pretty cool what he's done. Alrighty, so from our integral tables we know that this just equals root pi. Can you believe that? All of this just equals root pi, and that was the one on the outside. So now I just expanded it all again. So I expanded C, I expanded A, I got all of that. bit.ly dot, I think it's bit.ly/Gabortisavant. It's bit.ly/Gab savant. Yeah, I think that's what it is. All right, so we finally solved it. I'm a member. Yay. Hey, empty glass of whiskey. I love that. That is hilarious. It's in the bio. Is it? Oh, okay. Alrighty, so that's it. There you go. So that is the equation finally for this. This is the answer to this, which we tried to get right at the original. Right? All the way back here, we said that the fingerprint, so all of the possible fingerprints, equals 1 over the square root of 2 pi by the integral of the wave function at time 0 multiplied by e to the minus ikx. Right? So as I was saying, right, you know, right at the instant where you let the quantum particle go, it disappears into a wave, this infinite wave. And you're like, where's the particle? I have no idea. Well, what we're going to do is we find all the possible wave fingerprints, as we said in the last lecture. Right? Those wave fingerprints, we need to find that equation, and we just solved it. We just found that equation. It is 1 over 2a pi, right, all to the 4th root, which is the square root of the square root, multiplied by e to the minus k squared, which is the fingerprint squared, over 4a. Right, we did it. So now this is the last part. The last part is, all we have to do is, now we're going to create all of the wave equations for all time. Now if you remember, right, look at this. Remember, this was the original equation, right? The original equation was x0, so that's 1 dimension of space, no dimension of time. This was a snapshot. Okay, so as soon as we let the particle go, right, the instant we let it go, we freeze it and we find out that wave function. But the wave function changes over time. So that's what we're trying to do. We're trying to find the wave function for all time, right? And so we know, right, from the last lecture that this is the general form of the wave function for all time. And there's that fingerprint function, right, that we had to find. But now we found it. We found it. It's right here, right? It's this. Where is it? This thing here. Okay, so we come back. Here is the wave equation for all time in 1 dimension of space, 1 dimension of time, which is 2 dimensions, right? Soon we'll do it in 4 dimensions, but at the moment just 2 to keep it simple. Okay, and here it is. So all we have to do is put that into here, and we solved our problem. Complete. Done. And now I'm going to show you what the wave actually looks like, right? And this might freak you out. Alright, the wave equation actually looks like this. I can show it to you. I think this pen has run out. Okay, so here it is. Right, this is just simplification algebra. You lost me at hello. Multi-dimensions. Oh no, there's definitely multi-dimensions, but I'm only doing 1 dimension now to keep the mathematics simple. But it's funny when you lost me at hello. I love those comments. Those are the comments I used to make at school, man, and get kicked out all the time. Anyway, all right. So here is the final thing, right? Just some basic mathematics. So this is the wave function for all time. Okay. It equals 2a over pi all to the 4th root. Okay. All to the 4th root. Okay, multiplied by e to the minus ax squared. Remember, a is like roughly sort of like the angular speed, you could call it, of the particle. X squared is like its location squared. Okay, divided by 1 plus 2 by this 2-dimensional number I, which is the square root of -1. Okay, plus 2i h bar, which is the pixel size of the universe, a again, and time, right, over m. Okay, and all of that is over 1 plus 2i h, which is the pixel, a angular, time over the mass, and all of that is square rooted. Alright, so there you go, we solved the wave function. Now this is actually not as complicated as you think. It just means that if you want to find the particle's location in one dimension, right, of space, and at any point in time, we get the spin, like the angular speed of the particle, right? We chuck it in there. We have the location, we chuck it in there, right? If we don't have the time, but we have the mass, we have everything else, we can find out the time. And if we have the time, but we don't have the location, we can find out the location. All right? So there you go. So what did we do? Thank you very much. What did we do? Once again, all we had is when we let the particle go at the beginning, we let it go, and we got the wave, right? We freeze it immediately, freeze it and get that wave. And then what we do is we rebuild the possible waves for all time. And to do that, right, we've got to get the possible fingerprints of all of the waves, right? And then we just work out the equation, the mathematics, and then right at the end, we've got the thing for all time. And that's it. So now we know exactly all the waves for all time, which is awesome, because then you can track the particle everywhere. Because if you can't track a particle, how are you supposed to build a mobile phone? How are you supposed to build quantum computers, right? Because you're going to lose a particle and then you don't know where it is. You're like, what the hell? It's like the best example, thank you. The best example is like, imagine getting a drop of water, right? And dropping it into the ocean. As soon as it goes into the ocean, where is it? It's just an ocean of water. How do you find it? Well, mathematics can show you where that drop goes and where all the potential locations it's going to go. So it's going to go down, then the current will move it this way, then it'll go that way. It's never going to go like towards Australia, for example, if the current's going north, for example, something like that. So mathematics can track all the locations of the particle over all time. It is phenomenally powerful mathematics, right? And here's the last thing I'm going to say, right? Thank you very much, Supernova. Here's the last thing I'm going to say that may blow your mind, right? The equation for the wave has this number in it, pi, right? Now, why is that important? Well, the number pi goes to infinity, right? The length of pi goes to infinity, and this universe has a limit in size, right? We have pixels, and nothing can exist smaller than that pixel in this universe. So we're made of pixels, right? How can you have a number? How can you have a number that runs for infinity in a universe that is finite? What does that tell you? I know what it tells me. I don't know what it tells you guys, but the equation for the location of the particle has a number that's infinite, but the locations are finite because we have pixels. We're made of pixels. That means, as far as I'm concerned, that the mathematics is more accurate than the universe allows. That means that the true location, right, of these waves, right, cannot be 100% represented by the universe itself. In other words, the universe is less real than the mathematics that describes the universe. That to me blows my mind. The mathematics, even though it's abstract, the abstract maths is more real than reality. So clearly there is something that exists outside of our little nothing of a universe, right? It's very humbling, you know, when you think of that. Hey, Abyss is back right at the end. When you think of that, you think to yourself, yeah, you see people fighting and getting upset over certain things, and I'm like, man, like we are nothing. We are nothing compared to what's out there. We're not even a nothing. We're a nothing of a nothing, you know? So there you go. Take from it what you will. And that concludes our lecture today on Gab Smacked. Don't forget, you can subscribe to Gabflix for your daily Gab fix. We've got Gab Unsmacked, which is all swearing. We've got Gab Smacked, which is all about autism and depression and anxiety. We've got Gab Life, which is all about eating and enjoying life. And they're all on Gabflix, which is bit.ly/GabAutisavant. Gabversity, where facts don't care about your feelings.